happen if we took the graph of the square root of x and rotated it around the x-axis? What would it look like? Okay, similar shape to a cone. Not quite a cone with rounded edges, kind of. But this shape here, does everyone kind of see what shape that would create? Well, we've got going all the way around. I'm not an artist, so you've been the best I got. But that would be the shape that we get when we rotate this figure around the x-axis. It would create a solid that looks something like this. Our goal for today will be to find the volume. Question: what would a cross section of that be? A circle? We would agree the cross section is a circle. Should we be able to do the exact same thing we did yesterday? Add up all the areas of the circles. What is the equation for a circle? The area of a circle is pi r squared. This is not a semicircle, is it? It's an actual circle. So I could integrate from 0 to wherever that stops. Where does that stop? Is it 4? It went a little past 4, but we'll stop at 4. I'm not exactly sure. So it's 0 to 4. Pi times r squared. I'm just going to move the pi out of the way. And would you agree those are perpendicular to the x-axis? What is the radius of one of those circles? What do you think? Just the square root of x, right? Now on the ones yesterday, a lot of times on the semicircle, we had to divide by 2 because the whole region was the base of the semicircle. So you got the diameter, but this one, the radius just is the height of the curve.
So it's just one line, it's usually just actual lines, the radius.
On this one. So that's what we're going to be doing today, and it's called the disk method. A lot of people teach the disk method before they teach volume, and I don't like it that way because I think that it makes you think the disk method is kind of the first thing and then volume. But really the disk method is just another case of volume in general. Integrating area gives you volume. Yes.
How do you know when you need to divide radius by 2?
You've got to draw a picture.
Like, I don't feel like I would know from that.
Okay, so this picture, what is the radius? Isn't it the height of the curve?
Just
And so I don't need to divide by 2. Now, if I go to a problem we did yesterday, here, where I'm doing semicircles perpendicular to the y-axis, right? The radius would only be half of that distance. Does that make sense? So pictures are important. When you come to my desk and ask me to help you with a volume problem, only a couple of you have done that, but what's the first thing I have you do? Draw a picture. It's not because I'm just being hard on you. You're gonna have to have a picture to look and see what you've got going on. Remember me telling you visual spatial learners are better at this. It's not because they're better, they're more willing to draw pictures because that's how their brain works. They may be drawing pictures in their head, but they're drawing a picture somewhere. Does that make sense? So whenever we revolve an area, we create an object that has circles for cross sections. The act of revolving makes a circle. Those make a three-dimensional shape. Using an integral, we can add together all of the circles to get volume. If we are rotated around the x-axis or any horizontal axis, the width of the disk, we're going to do dx because our circles are perpendicular to the x-axis. Our little dx is going to be the width of the disk. And then if we are rotating around a vertical axis or the y-axis, we will get a dy because we will be perpendicular to the y-axis. I think I have a little visual for you. So if you start with the f of x and rotate it around the x-axis, you will always create a three-dimensional figure with cross sections that are disks. This is a curve completely different than the one I started with earlier. Each cross section is a circle with radius f of x, the curve. And the volume is the integral from a to b of pi r squared. A lot of people find disks easier than yesterday, and that's why a lot of people teach them first. Because you're going to do the same function every time. Pi r squared will be the function. You don't have to think about what the function is. The next thing we're going to look at is called the washer method. Sometimes there are figures that we rotate that leave a gap in between them and the x-axis. So hold on, I'll move it back up so you can write in just a second. Let me show you the visual really quick. So if we start with two functions, f and g, and we look at the area between those two functions and take that region and rotate it around the x-axis, you still get a three-dimensional solid, but it has a hole in the middle. Would you agree with that? In that case, the cross-section is what we call a washer. Have y'all ever seen a washer in construction? It looks like that. How do you find the area of a circle with a hole in it?
Find the areas of both circles.
Find the area of the big circle and subtract the area of the little circle, right? So the area of our cross-section will be f of x, the area of the f of x curve, right? Pi r squared with f of x minus pi r squared with g of x. So this is an area of a cross-section. And so the volume is the integral from a to b of pi r squared of the outside curve minus pi r squared of the inside curve. I'm going to go back up and let you write. Okay, so steps for finding the volume of a solid of revolution. Draw the function or functions and determine the region that you're going to rotate. So step one, find out what you're even rotating. If you are not drawing a picture, you will probably get it wrong. Now, that picture could be in your calculator if it's a calculator problem, but step one, you really need to draw a picture. If the region is rotated around a horizontal line, you integrate dx. If the region is rotated around a vertical line, you do dy. If there is no gap between the region and the axis of revolution, then you're going to use a disk. If there is a gap, you will use a washer because there will be a hole in the middle of your solid. If you are using the disk method, it says carefully identify R and then use the formula. If there's a gap, then you must identify both the outside radius and the inside radius. I'll give you a minute to write that, and then we'll do some examples. Okay, so let's look at example number 1. Find the volume of the solid. So ready? created if the region bounded by the square root of x, y equals 0, and x equals 3. So the first thing I'm doing is drawing my region. It doesn't have to be a pretty picture, but enough to figure out what I'm rotating. I'm going to rotate that around the x-axis. Again, you do not have to be an artist. You just have to get the gist of where the circle is. I promise you I am not an artist. Here is an artist picture of what this looks like. It's kind of hard to see with the lights on. So you're getting a solid. So I'm going to ask myself some questions. I've got my picture drawn. Is there a gap between the region and the axis I'm rotating it around? No, so this is a disk problem. I'm going to use a disk. So I only have to pick out one radius, which is nice. And that one radius is the height of the curve. Does everyone agree? So this is that bell ringer. Square root of x is my radius. But remember, it's pi r squared. A lot of times people will forget the pi. Remember, you've got to integrate the area curve, which is pi r squared. From 0 to 3. Where did I get 0 to 3 at? Yeah, the region is going from 0 to 3. I could do that one without a calculator. Would you agree? So this is just x. The antiderivative would be 1/2 x squared. From 0 to 3. 9 pi over 2 minus 0. So the volume of that solid is 9 pi over 2 cubic units. Okay.
Will it tell us what units to use, or
If it doesn't, then just leave it as 9 pi over 2.
units?
You can put units cubed. Find the volume of the solid created if the region bounded by the square root of x. Same first part. Y equals 0 and x equals 3. Same region. Everyone agree with that? But now we are rotated around the y-axis. Does that change the problem quite a bit? So now I'm rotating that region around the y-axis. Question, is there a gap between my region and the y-axis? Yes, there is a gap. What does that mean? Good, there will be a hole in the middle, right? So this will be this three-dimensional shape. Again, you don't have to be an artist. You can tell I am not. But you've got an inside circle and an outside circle. Everyone see that? So I know the formula I'm going to be using is the integral of pi big R squared minus little r squared. And I am going to be dy. Why dy? I rotate around the y-axis. The pi does technically go with both. Since I put it out in front, I have it with both. If not, make sure you put it with both pieces, because you're doing circle area minus circle area. I am integrating from y value to y value. So 0 to this y value up here. Remember, the x was 3. What would the y value be when x is 3? Square root of 3. So I'm integrating from 0 to the square root of 3. Remember the limits have to be y values as well. What is my outside radius? So if I look at these circles on the outside, no matter where I am along the curve, what is the outside radius?
X squared or y squared?
3. Why 3? Yeah, does everyone agree that it's 3 units out? It's kind of a vertical line we're using. X equals 3 is that outside radius, right? So the outside radius is 3. Almost too easy, but would you agree all of those outside circles, you've got kind of got a cylinder on the outside. Inside radius is more complicated. Would you agree the inside radius is the x value of this curve? Well, x equals y squared. Everyone agree with that? So the radius of the little circle is y squared. Any questions so far? Yes.
Get the square root of 3 on the limit.
The x value to the edge of my region was 3. But remember, I need y values because I'm dy. So I want to go to 0 up to this top y value. So I can go find when x is 3, what is y? And so it would be the square root of 3. I can integrate this by hand. Are y'all okay if we don't do a bunch of by hand integrals today just for setup purposes? Okay, let's look at this. Now we have 2 curves, not just one. Find the volume of the solid created by revolving the area between the graphs of x squared and x plus 2, first about the x-axis. I went ahead and put the graphs up here, but could you have drawn both of those graphs by hand? Sometimes they will be calculator problems, ones you can't draw by hand, others they will be problems you can draw by hand, just depends. So this is my region. And I'm going to rotate that around the x-axis first of all. Johnny, will you turn the lights off for just a second? I want to show y'all the 3-dimensional image of that. So if you look to the right, you can see what the 3-dimensional image looks like. This is, everyone see that? Rotating this around the x-axis. We have an inside circle and an outside circle happening. Does everyone see the picture? Thank you. Okay. First of all, is there a gap between my region and the x-axis? There is a definite gap. Now, a lot of people say, no, there's not. They touch right here. If there is ever a gap, then there is a gap. You know what I mean by that? It's not completely flush with the place that we're rotating, then there is a gap. So, this is a washer problem. Since I'm rotating around the x-axis, would you agree my circles are perpendicular to the x-axis? So their little widths are dx. The outside radius. What is determining the outside radius, or the radius of that red circle there? The line. Everyone agree the line? So the radius of the outside circle is the line, which is x plus 2. What is determining the radius of the inside circle? The parabola, get that little bottom curve. Where am I going to integrate this from and to? Well, I need the edges of my region. And how'd you get that? Good, set those equal to each other. So x squared equals x plus 2, so, and that does factor. -1 and 2 are the intersections. Okay, any questions about that one? Okay, I'm going to switch it up on you. I want to rotate around a different line this time. I want to rotate around the line y equals 5. We've never done that before. But can we? Sure. This is where you will notice my lack of artistic skills. Let's see. We have parabola. I'm going to run out of room. Okay, so we have, is there a gap? Big gap. So we have a washer. Is it still perpendicular to the x-axis, though? Yes. So we're still dx. We can still use our intersections that we found. We just need to find our big R and little r. So the green circle, and I would work with the part that I didn't draw. You know what I mean by that? It's probably a little better, especially for those of you who are artistically challenged like me. So let's look at our outside circle, the red one. What is the radius of the red circle? 5, right there it's 5. What about over here? Remember, those red circles go along the whole region. 5 minus x squared. How did she get 5 minus x squared?
No matter where it is, it's going to be that.
No matter where it is, it's, if we had this part here, right? 5 minus x squared, does everyone agree that would give you the distance? The height. So you kind of see a top minus bottom thought process there. I know that's not big R minus little r is not top minus bottom. But to get that radius, we had to do a, so 5 minus x squared is the outside radius. The inside radius is that green radius. 5 minus the line. Does everyone agree? What is the line? Was it x plus 2? So in general, if you are rotating around an axis other than the x-axis or y-axis, you will probably either have the curve minus a number or the number minus the curve to get the distance between the two. And actually, if you did that backwards, the square would fix it anyway. Like if you had done x squared minus 5, incorrectly done bottom minus top, because of the square in the formula, it would correct it anyway. But you need the distance between those two pieces. Okay, you try the next one. Around the line y equals negative 3. Did everyone get to see the models? Disc and washer things? Again, if you come to my desk and ask me one of these questions, what's the first thing I'm going to ask you? Let me see your picture. Most of the time when people have a question on these, they haven't drawn a picture yet. You don't have to see the answer before you draw the picture. In fact, you probably won't. Again, we're taking this region and revolving it around the x-axis.
One more, Brady Kester.
We all agree there's a gap, which means this is a washer. So I need the big R minus the little r. Still dx, does everyone agree we still have perpendicular to the x-axis cross sections? Big R, well, let's look. And remember, use the region that you didn't draw. It's a little easier. So use the curve up here. It's the line minus negative 3. Everyone agree? Or the line plus 3, if you'd rather think of it that way. Was the line x plus 2? Is that right? Minus negative 3 or plus 3. That is my outside radius. My inside radius, the blue circle, x squared minus negative 3. Everyone agree with that? This distance here. X squared is the top, and negative 3 is the bottom. So x squared plus 3. And I'm just going to rewrite since I ran into my... Negative 1 to 2 was our limits, is that correct? Because it's always edge of the region to the other edge of the region. And the region hasn't changed. I've just been rotating around different axes.
Maybe we could do this graph on the Y.
I rotate around the Y. Yeah.
Would it just be like overlapping?
We will. It'll be quite yucky. But we will, actually. This particular one is hard to rotate around Y, but we will. Okay, any questions about this one? Uh-huh. Now you're rotating around this line.
So you have to move it.
So it's, yeah, swinging big all the way around. So this looks like a rotation around the x-axis.
Okay, so you just
Yeah, it rotates real big. All right. Well, speaking of rotating around a Y, Grant asked, will you hit the lights again for a second? So this one, we're going to rotate now around the line x equals 7. So you can see way over here, rotating around that line, x equals 7. Want to see that? So way over here, we're going to rotate. It's going to look like this. On this side, it's a rotation all the way around x equals 7. So we will have an inside radius and an outside radius. So we have the outside circles. I want to carefully draw 2 of those. And then we have our inside circles. And we are rotating around the line. And I don't know if I have it as far over as I need to, but we are rotating around the line x equals 7. Thank you, Jenny.
That'd still be considered rotated around.
Let's look. Are our cross sections perpendicular to the x-axis or the y-axis? Y-axis. Everyone agree? So this time we will be a dy. Is there a gap? There's a big time gap. So we are doing a washer. Intersections will change, won't they? They won't change. The intersections are the same. But would you agree I'm going to have to integrate from 0 up to this y value here? Well, what is that y value? The x value is 2, wasn't it? And then 2 plus 2 is 4, or 2 squared is 4. Either way, you can convert that to a y value. However, there is a problem. We probably won't finish this problem today. We'll finish it tomorrow. Look at the red circle. Would you agree the radius on the bottom half of this picture is different than the radius on the top half of this picture? I'm going to have to split this into 2 different integrals. We will do this one tomorrow. Yes.
What's the top or your bottom?
The bottom of the region. What's the y value at the bottom of the region? And we'll do this up tomorrow. We will grade both area and volume tomorrow. We will not grade this
keep track of the two or three chambers for today.
Everything. We keep it. We are grading Power Series 1 through 4, and we're grading AP 1 through 6.
On our paper,
Yeah, I said 1 through 6 yesterday, and I'm going to stick to it since I said it.